Welcome to the mountains of southeast Tennessee. We're here in Etowah, which is just north of our headquarters in Benton. And we're going to talk about how model trains are made. My name's Shane, and I'm blessed to lead a truly talented team who love to make model trains. You might think it's a really simple process. In fact, we've even had people say, all you do is say we want to make this locomotive or this freight car, we send it to our factory, and sometimes later it magically comes out exactly like we wanted. Well, that's the furthest thing from the truth. It's a really complicated process. We spend a ton of time in the research phase getting everything right from the dimensions to the colors. It's tough to make railroad, road number, and era-specific trains. So you know what? Why don't you grab some popcorn, your favorite beverage, sit back, relax, and let's enjoy together how model trains are made. The first step in the product development process is deciding what we're going to create. Each year, we have a strategic planning meeting to chart our company's future direction. During this time, we review the current all-new product plan. Next, we review suggestions gathered from emails we receive at ideas@scaletrains.com, as well as social media, trade shows, and more. Utilizing our decades of industry experience, we select new projects and add them to the development schedule. Usually, several months pass before we're ready to prepare the research package. In the interim, we're gathering prototype documentation including builder's drawings, general overview drawings or GODs, roster information, paint and lettering diagrams, photos, and much more. During the research phase of the Big Blow Turbine, founders Mike Hopkin and Paul Ellis sat down with our friends from Trainmasters TV to describe this process in the video documentary series, Scale Trains, Big Dreams.
The plan we're looking at is a GOD, that's a general overall dimensional drawing, and that's something that GE would have used for the basic construction. It gives all of the major dimensions, and it's a great place to start. If you've actually got to go out and measure a real locomotive or a freight car, if you're looking at something that's 40, 50, 60 feet long, it's awfully hard to pull a tape measure out that far and keep it tight and straight and get an accurate measurement. So those drawings are really a great help to get the major dimensions. It's great for the factory and the engineering team to be able to lay out the basic footprint for this model.
Turbine tenders got swapped around, so you had variations there, and even the A and the B units, even those got swapped around occasionally. When an A unit got swapped, it would be renumbered to match the B unit it was now mated to. And so that way you get mismatches between the dynamic brake equipment, which is another detail that changed between the two orders that they got.
I am Executive Product Development Manager. That involves doing the research, whether it means research can be books, magazines, photographs, actual field research, measurements. Some people consider me a rivet counter because I really like to focus on the fine details of different locomotives and freight cars, and I just try to bring that knowledge and that passion and desire of accuracy to our endeavor here with Scale Trains. A matrix is basically an Excel spreadsheet that I put together with multiple columns and rows covering all the basic differences between the different locomotives in that group. A row will cover, a block of units, and okay, here's the first order of units numbered 1 through 15 or so forth. And then the different columns would highlight different details, like this unit was equipped with this style of radiator, this unit was equipped with this type of tender when it was built. We use that for both production to help make sure that the factory gets the details correct, and as well as for artwork to help the artist understand, okay, this road number that he's doing, this should have this type of horn, or this horn should be in this location, or it should have this type of radiator, and so on and so forth.
We basically put together a specification package for the engineering team over in China, the variations that we're going to want to build. Then the engineering team starts and they'll work on the first original drawings. Obviously the tooling for projects like these is very expensive. And so we're looking for as many road names and paint schemes and variations that we can use that tooling for. Roster shots are great, but most rail fans or enthusiasts that are out trackside taking pictures don't take the kind of pictures that a manufacturer needs to be able to build a model. And so what we've found is that we've actually got to get out there and document it, measure it whenever possible. We've got to have that kind of detail. Typically, those of us on development are looking at it from the standpoint of what is the most easy project to research? What do we have information on? What's a, you know, where can we most easily and most readily, you know, obtain the information required?
When completed, the research package is submitted to our design team in China. We have several full-time design engineers dedicated to our company exclusively. If builder's drawings were submitted with the research package, they're scanned into the CAD or computer-aided design software and become the basis for the model drawings. The dimensions on the drawings are then compared to field measurements to ensure they both match. Oftentimes, changes are made during manufacturing and there are discrepancies. When this occurs, we have to determine which dimension is correct. If builder's drawings are unavailable, the model is drawn line by line in CAD using field measurements. As you can imagine, this takes much more time. A drawing is created for each model variation. For the ES44, there are numerous detail differences like cabs, antennas, dynamic brake configurations, grille arrangements, trucks, and on and on. Altogether, we've created drawings for over 60 different versions. The first round of CAD drawings for a new freight car are usually completed within 4 months, and a new locomotive within 6 months. Once we receive the engineering drawings, our product development team reviews them and works closely with our designers to make revisions so the models are as accurate as possible. Depending on the complexity of the project, this back and forth can take several months before the final drawings are approved to create the tooling. Next, work begins in China on the CAD design for the steel molds. In the US, our artists start applying paint schemes to the engineering drawings. Joe, another one of our founders, explains how art is created.
It's important for us to submit artwork to the factory for 2 main reasons. Number 1, without it, they would not be able to produce our product. Number 2, they use that artwork as a guide through the production process to create an accurate model based on the information that we've given them. Having artwork when we announce a product is important because it allows the customer to see what that model is going to look like once it's produced. Also, it gives fans of the prototype the ability to chime in and let us know if we've missed anything so we can produce an accurate model.
Now that the research phase is done, it's time to pack our bags and head to our factory in China, where we take a closer look at the design phase, which is the CAD drawings, as well as tooling. After nearly 24 hours of traveling, we arrived at the Hong Kong International Airport. This modern airport opened in 1998 and is one of the largest and busiest passenger and cargo terminals in the world. We picked up our luggage and caught the Airport Express train to Kowloon, where we spent the night and got some much needed rest. The next morning, we took a short taxi ride to the high-speed railway station where we boarded the train to mainland China. The train ride is a short 30 minutes northwest of Hong Kong. By car, it's nearly 2 hours. Along the way, we passed through Shenzhen, which is one of the largest cities in China. Our factory is located in the Dongguan province, which is an industrial area with many factories and small businesses employing the majority of the population. With over 45 million people calling the province home, it is one of the most heavily populated areas in China. When we finally arrived at our factory, we visited our engineering team to see the drawing progress for our upcoming new announcements. Behind this door is where the magic happens. We're standing in front of our design team's office. We've moved closer to our factory. That way there's more synergy between our design team, the engineers, and the molding department. So that way we can create the most awesome models possible. Let's go inside and see what they're working on now. As you look around the room, you'll recognize a lot of familiar faces. Go back to the Scale Train's Big Dreams video in 2015, and you'll see a lot of the design engineers are the same folks working with us today. And they're dedicated to us full time. That means they know exactly what we're looking for and what we want when we say railroad, road number, and era-specific detail. They work super closely with our team in Southern California, and they'll go back and forth as much as needed to make sure that all of our models are dimensionally accurate, that the features are correct, the details are right, and that way we can deliver the best models possible. So one of the big challenges with railroad, road number, and era-specific detail, especially on a locomotive like the SD40-2, are the countless variations. This locomotive's had a long life, and over that life, it's gone through many changes. As I'm looking at the locomotive in front of me, I'm looking at the non-dynamic brake version. Railroads like Missouri Pacific, Illinois Central, Rock Island all had this particular version. And so we're working on that tooling now. We're also working on the NS high hood version at the transition from N&W and Southern to NS. And we're working on things like the Santa Fe lower headlight and a ton of other versions, which you can see here on screen. And the reason it takes so long is because all of these have to be drawn individually so that we can make sure they're accurate for each railroad, for each road number, and for each era. So after we sign off on the final design, it's time to prepare to cut tooling. As you can see on the left screen, we're looking at handrails for the Tier 2, Tier 3 GEVO project. You see the handrail itself in green. You're going to see how the plastic is going to flow in blue. And the other thing we have to do is we actually have to look at the tool itself. You'll see there's all of these rods here at the bottom. Those are called ejector pins. And what they actually are going to do then is once this is molded, it's going to push that actually out of the tool, and that's how the plastic comes out. So as part of the design process, the engineer is going to actually draw the tool. And what we see here is a body shell tool for the Tier 2, Tier 3 GEVO. As he starts to peel back the layers, you're going to notice this is what's called a force slide tool. In other words, on a force slide, you're going to pull from the sides and the ends during the molding process. As he pulls it back, you can actually see the roof layer, and you also see these numbered sides. What those are inserts, and those inserts change from locomotive to locomotive, and that's what allows us to create the unique details. It could be grill arrangements, it could be dynamic brakes, it could be door arrangements, and then of course the other big thing you're going to see here are the ejector pins in the bottom. That's what's going to push that body shell out of the tool at the end of the process. And then over here on the left-hand screen, you're going to see there's actually 11 different bodies for the Tier 2, Tier 3 project. Each one of those is going to have inserts created so that we can get all of those unique details. So after the engineer has laid out all the parts in the tool and designed the tool itself, it's time to run simulations. As you can see in the screen in front of me, what's happening is this CNC machine is actually cutting the tooling or the electrode for the EDM process. The reason this is done is to make sure that everything works together, as well as determine how much time is going to be required in the tool shop. What that allows the tool shop to figure out is how much capacity they need to make this particular model. So now that the tooling is all laid out and we've ran the CNC simulations, it's time to cut tooling and electrodes. And that's what's going on behind me. Let's take a closer look. So in this particular machine, they're actually cutting the steel cavity. What we'll do is we'll get the rough cut or the basic cut of the steel tool, and the next process after CNC is we start to put in all that fine detail into the steel mold. So we just looked at the basic steel tool. So how do you get all that detail? Well, that's this step. The CNC machines are actually cutting the copper electrodes. These machines are so precise that they can get all those super details into our models. The next step is EDM, or electro discharge machining, and we'll show you how these copper electrodes are used. So earlier we saw the CNC simulation, and we just saw the CNC cutting some parts. So what are they cutting? Well, they're cutting the basic steel tool design as well as these. These are copper electrodes, and they're used in the EDM process we'll explain soon. What you're going to see is the CNC machine actually cuts all the detail of it, like this SD45 radiator fan, as well as the SD45 long hood. The process is working exactly the same for the Tier 2, Tier 3 GEVO project. What's absolutely incredible about this process is it literally takes thousands of these electrodes to create the tooling. As we pan over, you're going to see over 2,000 copper electrodes on the floor. That's only half of the 4,000 required to make the SD45. The Tier 2, Tier 3 requires a similar number. This is what allows us to create all that railroad, road number, and era-specific detail. So after the CNC machine finishes cutting the copper electrode, the next step is to burn the design into the tooling. As you'll see behind me, there's actually an electric current passing through the machine, down through the electrode, and into the steel tool itself. And it's that process that actually burns the design into the steel tool. So earlier we saw on screen the layout of the tool for the handrails. This is the actual handrail tool. It takes about 2 months from the time that tooling started to get to this point. You can of course see the handrail stanchions, you can see how the plastic is going to flow, and the tool itself. Once the tool is finished, They're going to go back and they're going to check the fit and the finish. They're going to make sure everything works together and go back and polish the tool so that the plastic is very sharp and crisp when it comes out of the mold. So now that the tooling is complete, the tool master is checking the final fit and finish. As you can see on this side, it's using a red, almost like a dye. And what happens is when the mold comes together, if there's any red in this particular part, that means the molds are touching each other. So what he's doing now is going back and using this tool to clean up the mold to make sure that when it comes together, those parts don't touch. So in the tooling process, they create a cavity and a core. As you can see, this is the negative and this is the positive. So when the tool comes together, it actually creates the truck. Here in my hand is one of the cabs for the Tier 2, Tier 3 GEVO project. As you can see, it's one huge chunk of steel. This is the same slide insert in 4 different versions for the Tier 2, Tier 3 GEVO project. In addition, you'll look at this fine detail right here. It actually took 5 copper electrodes to burn in this minute detail. So tooling is not only created for plastic parts, it's also created for die-cast parts. And as you can see here, this is the chassis for the Tier 2, Tier 3 GEVO. After the hard tooling is created, plastic parts are molded. Our product development team meticulously reviews these first shots for accuracy and fit and finish. Sometimes the CAD design does not translate well to the actual part, and tooling revisions are required. Similar to design, cutting the tooling and signing off on revised parts can take up to 4 months for a freight car and 6 months for a locomotive. Later in this video, we'll take an in-depth look at molding.
After we submit artwork, the next step in the process is to wait for a Deco sample, a model like this, fully assembled but typically not functioning. This is the first chance that we actually get to see everything in 3 dimensions to make sure that the factory followed our artwork, to make sure that our artwork was accurate, and then we can see it all pulled together right here. So when we review the Deco sample, we're looking for things like paint application. Is it smooth? Is it all the color breaks nice and sharp and clean? Printing, same thing. Are the edges sharp? Is everything clean? Are the colors accurate? Is the assembly done correctly? Are the correct parts used? Are they assembled correctly? Are parts straight? Is there too much glue, not enough glue? Are parts all being secured properly? If there is a problem, then what we will do is we will submit a Deco sample review form. On that form, that'll list any corrections, adjustments that need to be made. Also, we'll send supplemental art or updated art if need be. In the case of this model here, the Wisconsin Central SDL 39 number 590, when we first looked at the photographs, to our eye, the color of the striping appeared to be the Dulux gold. But once we got the models in, we photographed them, we put them on the web page, and the Wisconsin Central fans alerted us that actually 590 should use the lighter shade of yellow that's also used in Wisconsin Central. So in a case like that, again, we're going to update the artwork, going to change the color, we're going to send the updated artwork along with the DSR form that's going to indicate the color change. We're also going to alert the factory to any other corrections, adjustments that need to be made on the model. Once those are submitted, the factory will review them. They'll get back with us with any questions. From there, once that's all been resolved, we're ready to start production.
Once the Deco sample is approved, it's time for marketing to step in, and that happens right here in Tennessee. Our marketing team is going to prepare all the things you're accustomed to, like video and photography, the website, social media, and of course the trade show display. When everything's ready to go, we make the announcement. And for the next 30 days, we take pre-orders. And we use pre-orders to help us judge the interest in a model. If it's small, we'll only order a little bit of extra. If the interest is big, we'll order a lot of extra pieces. Once that process is closed, it's time for production to start. So let's pack our bags once again and head to our factory in China. After we place our purchase order with the factory, a detailed write-up is created for each department, including molding, printing, painting, and final assembly. This document is hundreds of pages long and takes about 30 days to complete. Once finished, subcontractors in the factory can start production. While our factory does most of the work in-house, some things do have to be subcontracted. Today we're visiting our PCB supplier. In my hand is an actual PCB board with all of the traces drawn. That's actually what is happening in the machine behind me. Let's follow the entire process and see how they're made. So the second step in the process is to actually add the electronics to the board. As you can see in front of me, it almost looks like a printer, and you'll see that the tape is moving as it goes into the machine. What it's doing is feeding each individual electronic component into the machine to be placed on the board. So the final step is to heat all the components up so that all the chases will flow and all the components are soldered together. This is the machine that does that, and it's several hundred degrees. The next step is to make sure all of the components are soldered correctly on the board, and that's what's going on behind me. After the PCB board is created, there's a few more steps in the process. Going on behind me, this gentleman's adding the 2 supercapacitors for the power pack. We're the only manufacturer including supercapacitors in all of our models at the rivet counter level and above. Also, we're soldering on the lights, and depending on the version, it depends on what lights are going to be soldered. So that's going to be things like headlights, number boards, in this case an SD40-2 with class lights, and then the final step is to make sure that all the lights work. That way when it's installed in the locomotive, everything works perfectly. When we started ScaleTrains.com, we challenged ourselves to push the limits of our favorite hobby. One of those limits was motors. We wanted to come up with a motor that was powerful, that could pull long trains, as well as silky smooth throughout the power curve. This is the motor we came up with. In my hand is the beginnings of a new motor. As you can see, the armature's here, it's been insulated, the shaft's installed, the commutator's there. The next step in the process is what's going on behind me. As you can see, she's running wire back from the machine and then actually spins the copper wire onto the armature. You know, it's incredible that something so small is so important when it comes to a locomotive. There's a lot of different processes that make a motor perform extremely well. Those include the number of windings on the armature, the type of wire, and the thickness of the wire. How polished is the commutator? But one of the most important steps is getting the motor balanced. Our motors go through 2 balancing processes. One you see in front of me right here is when the armature is totally complete. The last one is when the flywheels are installed. It goes through another balancing process. It's that balance that gives you that silky smooth control and that ton of pulling power. So here's the final step. This is balancing the motor with the flywheels installed. You know, we want to give our customers the absolute best value, and that's why we use the same motor in both the operator and the rivet counter brand. This gives you super precise motor control and stump pulling power. So this subcontractor makes the wheels on the train go round. I'm holding in my hand a piece of bar stock. This is the beginning of a wheel set. And what will happen is this is fed through a machine that's going to cut it to the appropriate length. It's going to cut the piece of steel down to the right size, so the flanges, and then it's going to put a hole in the wheel itself. The next step is to go out to electroplating, where it's going to put the black color on the wheel, and then it comes back here for final assembly.
In addition to making locomotive and freight car wheels, the metal supplier also produces the metal gear assemblies. Here, an arbor press is being used to insert a gear onto the shaft for a locomotive gearbox.
So we're here in the warehouse where our steel molds are stored. It's really important that the warehouse is dry and cool. That way the steel doesn't rust.
While subcontractors work on the electronics, metal parts, and more, manufacturing begins at the factory too. Molding plastic parts is the first step. Here we see a hardened steel mold for locomotive handrails. To ensure our handrails are straight, we create a handrail mold for each color. This allows for shrinkage when the plastic cools. The factory uses both virgin and recycled plastic. Plastic from screws and parts that do not pass inspection are fed through a grinder to make pellets, otherwise known as regrind. As you can see, the steel mold halves come together and molten plastic is injected into the mold. After the halves retract, the mechanical arm reaches into the machine, picks up the part, and places it in a bin. This is one of the few robots at the factory.
Most of the molding machines at the factory are operated manually. As you can see, the work area is neat and clean. The operator initiates each molding cycle and physically removes the part from the machine. He then inspects each part for what's called a short shot. He's making sure the plastic flowed evenly throughout the mold and formed correctly. On average, a locomotive body can be molded and inspected in about 1 minute. For a run of 3,000 locomotives, that's 3,000 minutes or 50 hours for molding. This does not include setting up and tearing down the machine for each body variant. After we finish molding, it's time to prepare the bodies for paint. In this particular instance, we're taking and we're making sub-assemblies. This is a -9 cab, but it works exactly the same way for all of our other products. For the -9, you've got a separate number board housing, a separate nose door, and what this young lady's doing is actually installing an etched metal plate. That represents a builder's plate. So when the production's finished, you'll have that nice shiny metal look. So if you've ever seen one of our rivet counter undecorated models, they look like Swiss cheese. One of the unique things that we do is whenever it's possible, we design our models so that there's a pin in the tooling. And what that means is every grab iron, every part is exactly straight. You don't have to worry about an air hole in one place or another. Sometimes though, there's holes that we do have to drill. We're drilling holes for snowplows. You'll also see us drill holes for things like horns, beacons, and other parts that are going to move on the locomotive or the freight car. So as you can see in front of me, the young lady is actually cutting away the sprues that are left inside the body cavity. The reason they're there is to help the plastic flow during the injection molding process. Now that the molding is done, the sub-assemblies are ready, and all the detail parts are there, it's time to head to paint. Let's see how they do it. Our factory uses an acrylic or water-based paint. Since we're mass producing models, an automotive style paint gun is used to quickly apply the color. This spray booth has a water curtain to catch any overspray. Once the body or part is painted, it's set aside to dry. So as you can imagine, during the production process, there are literally thousands upon thousands upon thousands of small parts that have to be painted. To speed up the process, what the factory does is they take masking tape and tape to these large trays. Next, they affix the plastic parts. The tray then goes to the paint shop where the appropriate color is sprayed. Once dry, it comes back, the masking tape's removed, and then new masking tape is put on, the part is turned over, and the other side is sprayed. This saves a ton of time in the painting process. What's in the box? Have you got a good guess? Well, if you said lift rings, you're absolutely right. These tiny lift rings, there's literally hundreds on this frame. Before they can be applied to the locomotive, this has to be painted, and then the lift rings removed. Can you imagine the tedious process to make that happen? So as you can see here, this young lady is actually putting grab irons onto this foam pad. And what that allows us to do then is when this goes to the paint shop, they can all be sprayed at the same time. Once it's dry, each one's taken out and the long leg is cut off so that they can be inserted into the locomotive. As you can see next to me, there are literally hundreds and hundreds of light bars. And to make sure the light shines in just the right place, check out what has to be done. So a bar is used and there's masking tape wrapped around the bar, and then the light bar is actually affixed to the tape, and then more tape is ran along the top. The reason for this is it makes sure that the paint doesn't cover the end of the light bars. Then they're taken to the spray booth, they're painted silver, and that way the light is going to reflect on the inside of the light bar and only come out on the ends. After the base color is applied, it's time for masking. So here the base color was yellow, and then we come back and we do the blue and the orange. In this case, we're spray painting the orange, and you can see there's the very crisp lines. That's created by the paint mask. We could even get the unique shape for the C in the chassis cap. So the body's inserted into the mask, and he's pressing very tightly to get those sharp, crisp edges. He's going to work his hand down along the mask to keep the pressure very tight. About every 5 times that a body is sprayed, he's going to have to take the mask off and clean it to ensure the edges stay sharp. Sometimes the level of detail is absolutely unbelievable. You know, as the guy who writes the checks, I have to wonder what product development is thinking sometimes. Take a look at this. This is a special clamp mask that's created to do this very tiny detail to paint the silver on this air filter. Now, of course, that's what makes our models unique and what makes them so awesome, but holy smokes, this process is unbelievable. We even go to a ton of effort on the operator model. In my hand is an SD40-2 cab interior, and at the very back of the engineer's side is a step. And my right hand is the mask, and what happens is it's inserted into the mask, and right here you'll see that step. When it goes into the paint booth, that's going to be sprayed so it's the appropriate color. Unbelievable the amount of detail we go to, even in the operator brand. So as you can see, there are a ton of steps in the painting process. Between each step, the bodies are stored on racks just like these. Next to me, the Chicago Northwestern SD40-2s and the BN SD40-2s. When the time's right, they'll come off these racks, they'll go to the appropriate paint booth so that they'll look just right when they get to you. So after painting, it's time for pad printing. This is when the model actually starts to come to life. Let's check out the processes and see how it works. Before we start printing, we have to create the printing plates, and it all starts right here. On this film, you'll see the road number for our upcoming flat car that hauls rebar. And the way this works is this film is transferred to a metal plate using a chemical process that etches it into the metal. Right here, we're actually looking at number boards for one of our locomotives. So we're often asked, why do containers cost so much money? They're just a box. Well, it's called printing impressions. There's a lot of work that goes into the printing process. Today we're going to follow a DM&E SD40-2 in the Mount Rushmore paint scheme all the way through the printing process and see how much work goes into making the model as accurate as it can be. So she's now loading a body onto the jig, and we're going to watch 5 colors be deposited on that body. In this case, white, blue, yellow, black, and green, and you're actually going to be able to see the Mount Rushmore logo come into vision right before our very eyes. Now she's going to remove the body from the jig, and she's going to take a very close look at it with a magnifying glass. This is to make sure that everything is registered. In other words, no fuzzy edges. So now that we've got the Mount Rushmore logo on the side of the body, it's time to add the red, white, and blue banner. Here in front of me, you'll see this machine's depositing 4 colors: black, red, blue, and white. Altogether, that's 9 different colors to create this unique logo. When it's all done, they'll reset both machines and do the 9 colors on the other side. So that's a total of 18 different printing impressions to get this one unique logo on one locomotive. So final assembly actually occurs on the production line. And on the production line, there's going to be at least 50 different stations with workers at each station doing sub-assemblies that come together to make the final locomotive. Here we're in a special room so we can get it up close and personal and see what's happening. This particular worker is assembling the DM&E SD40-2 cab interior in the rivet counter series. There's actually 7 individual parts that make up this particular part of the locomotive. You've got the front wall, the back wall, 3 seats, and the control stand on both sides. As you can see here, she's applying very small dabs of glue on the underside, and that way none of the glue will leak through and you'll actually see in the cab interior. If you're like me, you're a fan of all the hard work that goes into our models. Here we see dynamic brake and radiator fans on an etched metal frame. Of course, this has to be painted before it can be assembled. As we look down at the table, she's actually putting these fans on the DM&E SD40-2. Very delicately, she's placing the fan in the grill itself, and then she's going to take some glue and finally touch around the edges to make sure that it's not visible when the final product is ready. If you think about it, in our example of 3,000 locomotives on a production run, that's 5 fans per locomotive. That's 15,000 different fans that have to be installed before this shipment is ready to leave. Thankfully, our factory workers are highly skilled at building model trains because final assembly is a meticulous process. Every part is hand applied. A freight car can have more than 100 separate parts, and a locomotive over 400 individual parts. The HO scale big blow turbine has a staggering 800 plus parts. Using our example of 3,000 locomotives, that's over 1.2 million parts that have to be hand assembled. DCC and sound locomotives require even more testing. Of course, we're going to test the light functions. In this instance, we're looking at a rivet counter Chicago Northwestern SD40-2. We're going to make sure the class lights work so we can cycle between red, white, green, and off. We're also going to check the number boards, make sure they're lit, and all of the headlights, both front and rear. In addition, you'll notice the sound is off right now. That's because we can test the coupler clank, the bell, the horn, and those other sound functions. And we'll test the prime mover eventually. While it's quiet, we're listening for the motor, we're listening for the gear train, and also the drivetrain. If everything sounds correct, and the sounds are correct, as well as the lighting functions, it's off to be married with the body. The last step in the manufacturing process is final packaging. Each model is visually inspected to ensure it meets our high quality standards. Blemishes are touched up and fingerprints removed. The model is then carefully placed in its package and prepared to be shipped to our Tennessee warehouse. So the final step in production is getting everything ready to ship. As you can see, the workers are rolling out the pallets in preparation for the container to arrive. All the pallets are shrink wrapped. They have straps on them. They've got corner braces. And this is to ensure the models arrive in the best condition possible when they get to Tennessee. This process will take almost 5 weeks from the time it leaves our factory until you see us open the doors in Tennessee. So what's happening now is the final step. We're loading the container in preparation to ship it to Tennessee. The forklift's going to come up, he's going to put it on the container. There's a gentleman inside, he's got the pallet jack, and what he's going to do then is move that container inside. So here comes the forklift. He's going to put the pallet inside. Once he puts the pallet inside, the other worker in the trailer is going to move that pallet to where it needs to go so that it safely arrives in Tennessee. So after the truck leaves here, it's going to make its way down to the port in Hong Kong. After a few days, it'll be loaded onto a ship and it'll make that long journey all the way across the Pacific Ocean, down to the Panama Canal, through the canal, and all the way up to Savannah, Georgia. At Savannah, it's going to be loaded on another truck and then come up to Tennessee. So the final step, your door first, is to shut the door. Ready? So the final step as we shut the door is this will go to customs in China. They'll put this bolt on it, and when we get to Tennessee, we'll cut it off. So here comes the truck. As you can see, it's a tight squeeze as he's leaving the factory. And as the truck passes by, here comes our last side of the container as it makes its 5 to 6 week journey to Tennessee. We wish it bon voyage. Well, this has truly been a journey to learn how model trains are made. It's been a ton of work, as you can see. We followed everything from the big blow turbine to the SD40-2 to the SDL39 and of course the ES44 project. A lot of this video documented the ES44, and the video footage from our factory was shot nearly a year and a half ago. That model's on the way to us now, which means that whole process was about 2 to 2.5 years. As you can see, a ton of work goes into making the best railroad, road number, and era-specific models. We hope you've enjoyed this video, and if you have, be sure to subscribe to our YouTube channel and ring the bell to be notified when we post new videos. We certainly appreciate you tuning into How Model Trains Are Made.